And then we come to axiom number 2. So axiom number 2 is the evolution axiom. The wave function psi of xt, representing, say, representing a system with a time, okay, that's just not system, is a solution to the Schrodinger wave equation. Okay. So what is that equation? We all know it's a complex equation. It has a time derivative, which is first order in time, which is important for probabilistic interpretation. And then on the other side, we have the Hamiltonian operator, which is minus h squared by 2m, nabla squared, psi of x of t plus vx. For now, we are taking systems which are independent of time, okay? It doesn't have to be. This can depend on time. But for our sake in this course, no. So we actually don't have to say how it depends on time and space. Okay, so this is the Schrodinger wave equation. So this is a linear PDE, but it's not relativistically invariant, unlike some other PDEs we know of. Do you know of any PDEs that are relativistically invariant in physics? PDE means partial differential equations.
Simple harmonic motion.
Is that relativistically invariant? Also, the simple harmonic oscillator, that's not a PDE, that's an ODE.
Is Maxwell's equation one of those?
Correct, correct. Maxwell's equations are all first order PDE. They are the time derivative and the space derivative are first order. And they're not written in that way, but they're actually relativistically invariant. And there is a way of writing Maxwell's equation in a relativistically invariant way in terms of some mathematical objects called differential forms. So there's a funny story about a Bangladeshi and Maxwell's equation, which I think I should tell you. So one of my friends, Mahbub Majumdar, when he first came back to Bangladesh, he applied for a job to teach at Dhaka University. And in the interview, he was asked by a senior faculty member of Dhaka University to write down Maxwell's equation. Mahbub Majumdar wrote down Maxwell's equation using the language of differential forms. But the guy who was asking him the question had no clue about differential forms. So he failed him in his interview because he thought that Mahbub Majumdar did not know what Maxwell's equations were. Okay, so this is Bangladesh, unfortunately. Yeah. So Maxwell's equations are good examples of linear PDEs. Okay.
So he wrote the 4 equations in only 2 equations, right?
Exactly. There are only 2 equations. You can do even better. If you define something called a vector potential, so you have a 2-dimensional rank 2 tensor, and you can define a vector potential called A, which is a rank 1 tensor. And if you define this, then, so the Maxwell's equations become del mu f mu nu equal to some constant, you can say 4 pi, and J mu. J mu is a 4-dimensional current. The charge density is the 0th component, and the 3-dimensional current is J. So these becomes two, the Maxwell's equation which have sources. The other two Maxwell's equation, they actually, in this language, they actually become an identity, okay? So it's just an antisymmetric, this means an antisymmetric derivative, okay? So because it's antisymmetrized, if you write f in terms of this, it's already antisymmetric in mu and nu, and because partial derivatives commute, partial derivatives are symmetric if you have two partial derivatives. So antisymmetrizing those indices give you 0. Okay, so anyway, that's a side topic. So let's talk about Schrodinger equation. So they're linear PDEs, right? So because they're linear, that means that if, say, psi 1, x and t, and psi 2, x and t are both solutions to the Schrodinger equation, then so is their linear combination C1 psi 1 plus C2 psi 2, where C1 and C2 are constants, okay? They are, I should say, complex constants. Okay, it's a very simple argument. If you have a matrix and V acting on V gives you 0, and say V and W acting on W gives you 0, then if you take the linear combination C1V plus C2W, acting on A, this will also be 0. It's as simple as that. However, the linearity of the Schrodinger equation is extremely important physically. It's the key to the importance of, say, Fourier analysis to quantum mechanics. Okay, so so if you have a solution to the Schrodinger equation of the form psi of p xt of the form of a p e to the power minus I by h bar p dot x minus et, then the linearity means that this thing, psi of x of t, which is 2 pi h bar to the power square root of 3/2, this thing, a of p, integrating over all these guys for different values of p, is also a solution to Maxwell's equation. Okay? So that was the linearity of Maxwell's equation. There's another, although quantum mechanics in its modern form were discovered in the 1920s, linearity has a very interesting consequence, which was only discovered in the 1980s, and that has to do with the fact that the no cloning theorem. Okay? So you can show that. I'm not going to go into that because involves a little bit more of a machinery, but it's a few lines of algebra that if you try to make a quantum device, so it's a quantum Xerox machine, say, and you essentially, there's an input and there's an output, and you want this device to output the input state as well as a copy of the input state. So, but of course, you don't know, like the state is general, right? I mean, it can be any state. If you say such a device exists, then you can show that by linearity implies that such a device cannot exist, okay? So that is an important result in quantum information, which depends on the linearity of the Schrodinger equation.